Good morning, everybody. It's early. Thank you for being here. So I think I'm going to talk here because nobody will see me behind the podium. So it's my first ICRA, and I should say that I'm positively surprised, from my personal perspective, how much human motor control and human-robot collaboration is presented here. So I'm coming from human motor science, motor neuroscience, and like most of the people in my field, we have started with unconstrained movement, thinking of very simple movements, how potentially the brain can manage the complexity of the human system and perform very simple things like reaching, extending the arm, etc. In my own history, I've then gradually transitioned to bimanual coordination, to interacting with object and increasingly more complex objects that start to have their own dynamics, increasingly and most recently towards interacting with other people and machines. And I think actually this transition is reflecting human evolution, right? Starting from upright stance, moving their hands, moving with very simple handheld objects to objects that increasingly have more geometric configurations, to those like a hammer, or to those that have their internal dynamics such as lassos and whips. And now we are at the point where human-robot interaction becomes a very critical theme, where the tool, the robot, starts to have its own control, not only passive dynamics. So with that evolution, I want to just pick the current work, which is on manipulating an object with internal dynamics. So to sort of give you the intro here, we interact with objects and constraints all the time. Driving a car, opening a door, turning a key in a key lock. But then we also interact with many complex objects, such as this morning probably taking a cup of coffee to your breakfast table, or if we look at a little bit later in the day, slightly more complex, carrying a few more of these dynamically complex objects, to fancy things like, well, cracking a whip. Now, I've used this video many times, but I just can't stop getting excited about the fact how humans have become adept in manipulating a whole variety of objects, not only with their hands, but also with all parts of their bodies, and this example of the ribbon with objects that have immensely complex dynamics. So how do we do this? Well, just a glimpse in robotics. Okay, it moves on to straight into humans. Let's look at carrying a cup of coffee. However, this already is a very, very complex scientific problem, because the cup, well, and the coffee inside, that is fluid dynamics. And this is not my expertise, so I made my life simple. And we model the cup of coffee in the most simplest way, namely reducing it to a two-dimensional arc with a ball rolling inside and transporting it on a horizontal line. Couldn't be simpler, but it still maintains the essence of the problem, that when you move the cup, the ball gets into motion and the ball acts back on the hand. And actually, as we'll see, that can create, depending on how you carry that cup, that can create very complex interaction forces that are actio-reactio, there's no time delay, that have to be preempted, compensated in very intricate ways, such that you don't spill your coffee. So here is the model of the task. In fact, we use the very well-known control problem of moving a cart on a horizontal line with a mass and a pendulum attached to it with a massless rod and a bar that describes the circular arc. And as you saw, we use that arc that the ball describes visually as the cup and this becomes a rolling ball. In our virtual rendering of this task, all we display is what you saw before, the arc and the pendulum bar. The human interacts with this cup, moving the card/cup or in task contexts that are then our experimental interrogations as to how humans control this object. Equations of motions are here, are straightforward, only describing the object, the card and the pendulum, with an interaction force. So, to start, here is our task as the subject sees it on a screen. The subject holds the haptic master robot, which creates a haptic interface such that you move the cup, but you also experience the forces that the mass of the ball acts back on your hand. Now, in the first experiment that I want to describe here, which was our first exploratory experiment, was where we contrasted two task instructions. The one was move as fast as possible from left to right, don't lose the ball. The second task was move the cup from left to right in a target time of 2 seconds, which was a comfortable time, because we wanted to contrast performance in the limit case as fast as possible, and in the case where the subject could find their best, safest solution. So to begin, let's just look at the performance metric in these two types of instructions. The left shows the target time task, and the right the minimum time task. And the task criterion was the temporal error, given that they should do it in 2 seconds, and minimum time was, well, how fast could they get? And both of those performance criteria show an exponential time course, which is very typical, representing that the human learns. It is not something that you can do from the first trial, but you get better with it. So there are the typical learning curves. That is just baseline here. Next, we looked at what everybody in movement science looks at, namely the motion of the hand, the position and the velocity profile of the hand. So in most of these unconstrained cases, when I'm gesturing in midair, point-to-point movement have a bell-shaped velocity profile satisfying minimum jerk, maximum smoothness. Now, this very simple extension of a point-to-point task already shows us that the velocity profile of the hand no longer has the smooth bell-shaped profile, but rather has little kinks in there, which obviously now, when we think about it, come from the forces of the ball acting against the hand. This is the 2-second target time where we have that little hump here, and this is the as fast as possible where you also see some humps, including that the profiles have a change, getting faster and thereby better. And the ball trajectory here shows this double humped profile. So in this very simple task, we already have in quotes, violations of what is otherwise generally assumed to be truth. So no bell-shaped velocity profile and a bimodal and a very variable ball trajectory. So now our next question is, how do subjects transport these objects? Do subjects choose safe solutions? What is safe? What is safe here? Well, don't lose the ball. The ball stays inside like this, and the ball escapes when the ball angle exceeds what we call the escape angle, the rim of the cup. And again, we have to extend what we have done in our area of human movement control from what has been a safety margin, typically the difference between, say, grip force and load force, or just a difference in height. For example, here, the difference between the ball angle and the escape angle, but that's not sufficient anymore because we're moving the cup, and in fact, there are two energies that need to be considered in order to evaluate how close is the ball from the rim and losing the ball. And the three components here are the kinetic energy of the ball height, the potential energy, and then an additional energy, what we have called pseudo energy, which comes from the moving reference frame, that is the hand moving the cup and the ball. Now, with a couple of transformations that I will skip over the details, we calculate the escape energy of the ball and then an energy margin, EM, that is normalized by this escape energy, which becomes a metric that we can calculate at every moment in time to see how close is the ball to actually skipping out of the cup. Looking at these traces here in our two conditions, target time 2 seconds, minimum time, this is the time course, and the red and the black trajectory are these energy margins that we calculate at any moment in time, and 0 is escape of the ball, and the red line is late in practice and black is early in practice. And in the target time, you see that late in practice, the energy margin increases, is higher here than early, so there they have time to maximize the cushion of not losing the ball. Whereas in the minimum time, the energy margin becomes smaller in trade-off against shortening the time of performance. So it's a very fine-grained, continuous measure that then we can use to evaluate how safely do subjects move the ball. Now, safe is one way of looking at it, but let's extend that concept of safe to invoke stability. Stability is a very encompassing concept that you can calculate mathematically in many different ways. Now, how could we invoke stability in this task? Stability is appealing because if we set up a dynamic system that has stability, then errors, small errors, and intrinsic noise attenuates itself. That's the nature of a stable system with an attractor. So we explored how we could evaluate whether subjects create this human object system that has stability to sort of offset some of the corrective actions to the system itself. So how can we evaluate whether subjects exploit stability that this joint system might afford? In this point-to-point task, we don't have an attractor where we might be able to do Lyapunov stability analysis or even local linear stability analysis. So what do? Well, we turned towards an extended and more recent development of stability analysis, which is called contraction analysis, developed by Slutin. So firstly, how do we go for stability? Here, we change the task in that we set up a little perturbation or a speed bump, where subjects had to safely transport the cup over this speed bump to the target box. And this early trial, you see that the subject loses the ball. In a later trial, they tend to manage this speed bump, and mind you, there is no vertical direction. It's virtual, so you just go through that force that you encounter. And in fact, we set up two conditions, one where you experience a resistive force and one where you experience an accelerative and assistive force. So what we did here was this is here, just exemplary profiles. Here is the speed bump with an assistive perturbation where the cup velocity over position starts to get this jerk and then settles. And in this case, there is a decelerative or resistive perturbation on the cup. And here is what we did. We conducted contraction analysis on the object, on that card pendulum system, and which looks at exponential stability of adjacent trajectories to see whether they converge or diverge. In this analysis, the summary is that we display here in the state space of that system, we identified these sub-areas or volumes where the system is convergent. So if subjects are able to exploit stability or convergent properties of the system, they should develop a trajectory that travels through these golden ellipsoids. Early in the trial, the trajectory evolves like this. P minus is when they encounter the perturbation, B plus when they are over the perturbation. And in a later trial, you will see how the trajectory just enters the volume when it encounters the perturbation and exits it again. So with this summary, I think we can make our first conclusions that subjects exploit stability, i.e. convergent regions in state space to manage that perturbation that they encounter. Moving on, we only looked at point-to-point movements where the richness of the dynamics of that cup pendulum system doesn't yet come out. So in the later two experiments, we looked at continuous rhythmic movement of the ball and cup, like this. Oh, you already saw it. So then we went back to the model to sort of understand what might happen in that system while we're interacting with it. So using inverse dynamics calculations, we derive the interaction forces that are necessary to achieve a sinusoidal cart position. We simulated those with all different initial ball angles, angular velocity was set to 0. So we did a very, very broad simulation sweeping through all these different initial conditions for the case that subjects performed 1 Hertz with a given amplitude back and forth. So on the left, you see a very complex interaction force that is needed to achieve a smooth cup position and the ball angle stays within the boundaries of the scale. On the right, you see a different initial angle of the ball, and it looks simpler, but still has 2 frequency components. So what we did to summarize that behavior of that simple ball cup system is we ran all of these simulations, and we summarized each of those, the complexity of the interaction force, by strobing the interaction force at the maxima of the cup position, and then looking at this marginal distribution and plotting this over the initial ball angle here. Now this marginal distribution corresponds to this piece here, and this one, much simpler, corresponds to this here. But interestingly, we see a structure which is very reminiscent of a bifurcation diagram, which is the signature of a nonlinear system that can develop chaotic trajectories. So, chaos is unpredictable. So now we have simulated and given evidence to show that this very simple system can display unpredictable trajectories. So how, in this physical interaction with a system that is potentially unpredictable, how can we manage this? Well, let's take a look and look at this experiment where we asked the subjects to move back and forth. And we asked them to move between those 2 targets and to choose their preferred frequency of going back and forth. Looking at the histogram of the chosen frequencies, you see this histogram here where there is a very pronounced bimodal distribution. Now, this is again telling us that highly likely, we infer that the system now has not only 1, but has 2 resonances, and the deep dip between those 2 peaks in the histogram is probably where the anti-resonance is, defined by the natural frequency of the pendulum. And so, seeing this, we extended our model, which so far we have only looked at the ball and pendulum or the discarded pendulum system, and we set up a control system that we regarded as simple as possible, that has a sinusoidal input force, but importantly, it has an impedance associated with it here. Now, using this model system and estimating the stiffness and damping values, which I can tell you offline, we then actually can make predictions as follows. How do subjects set up the system? Do they maximize predictability or minimize force? Minimize force, everybody talks about minimizing effort, minimize force of sorts. But given the unpredictability of the system, the potential unpredictability of the system, our alternative hypothesis was that we interact to make the system more predictable and thereby enable better control. Predictability was quantified by the mutual information between the input force and the object dynamics. A kind of nonlinear correlation measure where the higher the mutual information, the more predictable the system. Using simulations and plotting the data, we arrive at this summary graph. So for different frequencies with different stiffness and damping values in this three-dimensional plot, we colored the areas, and we is Pauline Maurice, who you just heard in the introduction. We colored the areas in this space with this kind of pink, where predictability or mutual information is above a certain value, high, and each of those blue points is a trial which also is characterized by a given frequency and the estimated stiffness and damping values. I think this, while it's a three-dimensional graph, it's non-optimal how it's presented. I think you do see what we want to show, that is the trials are in those areas which are more predictable than others, and conversely, if we do the same simulation and predict those solutions with lower force below a certain threshold, which are here colored in green, you can see that this very same set of data, the same set of blue dots, are actually in those areas that do not minimize force, but maximize or increase, favor predictability. Now, this is non-trivial because minimizing effort or force is something that we always invoke in human movements, and predictability becomes a concept because we're dealing with this complex system. Moving on, last experiment here. Now we have a nonlinear system. It's not very nonlinear, but the pendulum creates a nonlinear element in that system. So to what degree is the challenge in the system due to the nonlinearity, the pendulum, or how much easier or different would it be if we just have a mass spring system, and there are three other studies that have looked into manipulating a linear mass spring system. So we modified our simulation to only present linear forces, and we asked three questions. What is the role of the anti-resonance that we identified earlier in the linear versus the nonlinear system? Do subjects maybe linearize the system, i.e. lower the amplitudes of the pendulum to what everybody might think interacting with a linear system is easier? And again, how does force versus predictability look like in this linear and the nonlinear system? Okay, same experiment, choose your frequency. Let's take a look in both the linear and the nonlinear case, the frequencies that subjects chose. Up here, we see again this very pronounced bimodal distribution with, well, the anti-resonance in between, whereas in the nonlinear system, we see the anti-resonance much less of an issue than here. So while this is very similar to the previous experiment, here we have more subjects and more trials, and we do see that that anti-resonance is there, but in the linear case, it really is a marked place where subjects don't want to go. Why? Because in the linear case, invoking or getting at this anti-resonance, which basically stalls the system, is a simple sinusoid, which they very easily get at, and then things happen they don't want to have that happen. Whereas in the nonlinear case, the input force that achieves that stalling of the motion is a relatively complex periodic, multiple periodicities. And that is something subjects don't get in so easily. So counter expectations, the anti-resonance, which is sort of a real barrier in the nonlinear, in the linear system, is not so much a barrier in the nonlinear system, i.e., well, in some case, the linear system presents more things to consider, not to go at than at the anti-resonance. Next, we look at the forces that subjects exert in both cases. And here is the anti-resonance, and you can see that in the linear case, there is actually higher forces than in the nonlinear case, which remains much lower. Do they linearize the system with moving at smaller ball angles, amplitudes? Well, not in the linear case. Okay, that's fine. But actually not in the nonlinear case, right? There is not a pronounced attenuation of the amplitude. It's a little ambiguous, but bear with me. So, but the last one also is that the irregular or unpredictable behavior near the resonance is much more pronounced in the linear system, where we look at mutual information, which really drops down around the anti-resonance, saying that the system becomes very unpredictable. So, conclusion, counter, expectation, the linear system doesn't make the job easier. In fact, in some aspects, you could say that it makes the job harder. So that might be something to consider when you move from this scenario, moving with a complex object, maybe to a robot with some control, that linearization is not always the solution to simplification. So how much am I doing? Yeah. Okay. 5-minute time?
No, like no time.
No time. All right. So we have moved from our simple 2D system to a 3D system by actually creating a cup that is moved, and with a specific data acquisition system where we can estimate the ball and the cup and then have a 3-dimensional spherical pendulum. But I'm not talking about that. I want to conclude just with an image, so just to show how we can take this and can apply with the measurements that we have all our theoretically based analysis. But just to finish, as I was saying, that humans become increasingly more attracted to complex objects, we, and this is work with Neville Hogan, started to go beyond the simple pendulum and look at how humans manipulate complex objects, that is a whip which has wave dynamics and infinitely many degrees of freedom, partial differential equations. So how do subjects do this? And this is just a little bit of entertainment at the end here. We record the movements in the lab. We have motion capture. We take the whip data here and we analyze rhythmic and non-rhythmic behavior, having some first interesting results that rhythmic behavior is actually less variable, more stable, maybe. And the tip of the whip here, looking at the first PC of the whip markers, is remarkably tight, and tighter in the rhythmic case than the discrete case. So just as a teaser here, and the summary is that we interact with dynamically complex objects that introduces new control challenges that we do not see in interacting with a rigid object. This needs new analysis tools. Stability, I think, is an interesting core concept that you want to exploit in understanding human control. resonance structure of the object in the hand is something that shapes the strategy, constrains the strategies, and predictability is an important goal in a system that is potentially unpredictable. So with that, I want to close. And I do want to thank 3 people specifically here. That is Pauline, who partly worked on the project, and Megan also, who worked not quite on the project, but in lots of other things in my lab, and long-term collaborator Navajo. So thank you.
Thank you very much, Dagmar. We have time for one question while we switch speakers. So if you have questions, either go to the microphones or just speak loudly. Any questions?
Yes. Yeah.
Yes, that stability concept that you are using, that stability concept that you are using seems not to be a closed loop stability. I mean, there is nowhere a closed loop control here, right?
No.
Which is understandable, but then, so can you say a few words about that stability concept?
The contraction analysis that I showed you me?
Yeah.
Yeah. So contraction analysis is a differential way of looking at stability without knowing the attractor. So we used it, what I showed, to analyze the system without the control. So it was only looking at the object dynamics, where there is exponentially converging trajectories. What is currently going on, we also invoke what kind of controller is necessary to ensure this contraction of the trajectory. But this is ongoing work, and I'm not yet able to talk about this.